Hello and welcome to this video. This is EDEXCEL Topic 8 Energetics 1. This is a revision video. My name is Chris Harris and I'm from AlleryTutors.com. Now basically in this video, like I say, we're going to go through an overview of energetics for EDEXCEL in particular. And actually the slides that I'm using here, you can purchase these slides. If you just click on the link in the description box below, they're really good value. And you can actually use them for revision. You can print them off. You can use them to complement your current revision resources that you've got as well. Okay, so like I say, this is specifically for EDEXCEL and it matches the specification points as you can see listed on here. Okay, so we're going to start with enthalpy and what it is. So when a chemical reaction occurs, there's normally a change in energy. Okay, and so the enthalpy change of a reaction is the heat change in a reaction at constant pressure. Okay, it's given the symbol delta H. It has the units of kilojoules per mole. Now you can see here that we've written up the symbol that we use, and we see the big triangle. This means delta, it means change in. So H means enthalpy, and the little underground symbol that looks like here, it's called theta. This basically means the standard states and standard conditions. So all these reactions are done like that for comparative reasons. And the standard conditions are 100 kilopascals and 298 Kelvin, which is 25 degrees Celsius. Okay, endothermic and exothermic reactions. So reactions can take in or they can give out heat. Now we can get endothermic reactions. These are reactions which absorb energy from the surroundings. And you can see here that in this case we can set up an enthalpy diagram. And you can see that the reactants are lower in energy than the products. And because these are lower in energy, then we have a delta H that is positive. That means energy is needed to produce your product, so hence an endothermic reaction. And you can see here this is the reaction pathway that happens, and actually what we need is more energy than what actually is needed here, because we need the reactions to effectively, well, need the molecules to collide in order for them to react, and we call that the activation energy, which we'll look at later on as well. An example of this would be thermal decomposition of calcium carbonate. As you can see here, there's calcium carbonate forming calcium oxide and carbon dioxide. You can see this is an endothermic reaction. Exothermic reactions, these are reactions that release energy to the surroundings, so they're exothermic. Again, here's our energy diagram showing that. This time our products are actually lower energy than our reactants, so this means that delta H is negative. So this is an exothermic reaction. Heat energy is being released when we produce our products. So this is an exothermic. And again, here's our activation energy. So when we actually do this reaction, we need to put a little bit of energy in first, and then we get all the energy out. So it's a bit like when you're trying to light a fuel. When you're lighting a fuel, you need to have a spark. So you put that spark provides a little bit of energy initially, and then you get loads of energy out, obviously, as the fuel burns. And obviously that's going to be a classic example. So, for example, the combustion of ethane is an example of an exothermic reaction, and delta H is negative. Okay, make sure you know your delta H's. Okay, there's 4 types of enthalpy change that you need to know. The first one is the enthalpy change of reaction, given delta RH with the little theta symbol there. So standard enthalpy change of a reaction is basically the enthalpy change of a reaction according to the molar quantities in the equation under standard conditions. Okay, you must remember the standard conditions bit, it's very important. This one, which is delta neut H with theta, this is basically the enthalpy of neutralization, or standard enthalpy of neutralization. This is the enthalpy change when an acid and an alkali react to form 1 mole of water under standard conditions. So here's that 1 mole, but anything underlined you really do have to remember. It's emphasized for a reason. Okay, the other one is combustion, standard enthalpy change of combustion. This is basically the enthalpy change when 1 mole of a substance is completely burned in oxygen to make carbon dioxide and water under standard conditions. So again, completely burnt is here, and it's 1 mole of a substance. Okay, so not 2, it's only 1. Allows us to compare them. Okay, and the last one that you need to know is the standard enthalpy change of formation. And basically this is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. Okay, so there's a lot of standards here. So make sure you know these definitions, because they will get you marks and they may ask you to define, for example, the enthalpy of formation. You have to be able to write that. Look at the words that are underlined in particular. Okay, so bond breaking and bond making. Okay, so bonds are broken and they are made during a reaction. So bonds broken, we need to put energy in to break these bonds, and so we say that the energy needs to be absorbed by the molecule. Okay, so bonds are broken in the reactants. This is an endothermic process. Energy is needed, so it's delta H is going to be positive for this particular process. And you can see here, more energy is needed. Or if we have a lot amount of energy, this is positive. This means energy's gone into it. Okay, this is an example of a bonds broken format. But if more energy is needed to break the bonds than energy given out when bonds are formed, the reaction will be endothermic. Okay, so if we're using more energy to break the bonds, then actually the amount of energy that we're forming them, because forming them actually releases energy, as you'll see in a minute, then the whole reaction will be endothermic. Now, bonds made, so when bonds are formed, energy is released. Okay, so the bonds are made when products have been produced, and this is an exothermic process. So delta H is negative. And you can see here, here's our reaction profile. So delta H is negative. Products obviously lower in energy than reactants. So energy is released. And basically, again, just like before, if more energy is released when bonds are formed than what was needed to break the initial bonds, the reaction will be exothermic overall. And you're going to see a calculation example on the next slide showing that. Okay, and so remember, bond enthalpy is just the amount of energy needed to break 1 mole of a bond type in a molecule in the gaseous state. Okay, so make sure you know what bond enthalpy is. Okay, just a little additional note there. Okay, so bonds of the same type, they don't actually have all the same amount of energy. Okay, so for example, if we've got 4 CH bonds in methane, okay, they all have slightly different bond enthalpies. The energy needed to break the first CH bond will be different to the energy needed to break the second CH bond. Now, you might think, well, that's a bit strange. I thought every CH bond has the same enthalpy, but it doesn't. Okay, so if we have a look, here's the example. So if we measure the enthalpy of breaking all 4 bonds and divide them by 4, we get a mean bond enthalpy of CH bond. Okay, so for example, if we have a total of 1,662 kilojoules, okay, for 4 CH bonds broken in CH4, then the mean bond enthalpy will just be 1662 divided by 4, because we've got 4 of these, and that would give a mean bond enthalpy of 415.5 kilojoules per mole. Okay, now obviously these are slightly different, because if you break 1 bond and you have 3 CH bonds left, then the amount of energy needed to break them will change. And that's due to obviously the attractive forces of the carbon. It's not sharing as many electrons as it used to be because the bond's been broken. You've got a positive charge left behind. That's going to have an effect on the remaining bonds that are left behind. But that's basically just give you a little bit of an example. But enthalpy changes using mean bond enthalpy. You need to know this equation. So enthalpy changes the total energy to break the bonds minus the total energy released when we're forming these bonds. So we're going to calculate the energy change for combustion of methane. So you can see here that we've got our reaction written down here. And then we have our enthalpy data. So these are the bonds, and this is the mean bond enthalpy here in kilojoules per mole. Okay, so to break all of these bonds, that includes breaking the 4 CH bonds in methane and the 2, because you've got 2 of these, so it's 2 O2 bonds. These are the OO bonds here. And then we need to add them up. So we literally just do 4 times CH, so it's 4 times 435, which is 1740, and 2 lots of O double bond O, which is 2 times 498, which is that one there, equals 996. Add them up and we get a total of 2736. Okay, so that's an endothermic process. Now when we're forming them, obviously these are exothermic, so it's going to be 4 lots of OH, so it's 4 times 464 is 1856, and then 2 lots of CO, which is 2 lots of 805, which is going to be 1610. Because we're forming carbon dioxide, remember, and we have 2 CO bonds for there per carbon dioxide molecule, and obviously we've got 4 of these because we've got 2 water molecules. Total 3466 kilojoules per mole. So you can see here, total energy needed to break the bonds is less than the total energy released when we're forming them. So that means that energy is released overall in this reaction. So there it is there. The enthalpy change is minus 730 kilojoules per mole. So therefore, like I say, our reaction is exothermic. Okay, calorimetry. So calorimetry is used to work out the enthalpy change of a combustion. Okay, so basically how it works. You might have done this as well in school or college, where you have your fuel is burnt to raise the temperature amount of a specific amount. So you'll have a fuel in a spirit burner with a wick, and basically what we do is we weigh the fuel before and after burning, and what we're trying to work out is the mass, what mass of fuel has been lost, and we're going to use that later on. So the energy from the fuel is transferred into the water. Some is lost to the surroundings as well, and you've got to be very aware of that, because you've got to try and think of ways in which we can reduce that heat loss. So we'll put a lid on the top. Like I say, this prevents the heat loss, and windshields. We put these around the side here. This is to stop the draft from making this flame flicker all over the place. If it's flickering over here, that's going to heat the surroundings and not necessarily the water. So that's wasted energy. And the energy transferred, we can calculate it using something called Q equals MC delta T. We're going to see a little bit more of that in the next slide. And basically we can go further and we can work out the enthalpy change too, which is quite often what they want you to do. Alright, okay, so let's have a look at this equation then. So again, we're going to calculate the energy from calorimetry, and Q actually happens to be the energy. So this is the heat energy lost or gained, depending on what you're working out. It's measured in joules. M is the mass of water or the solution that we're using. Again, we'll show you what that means. That's in grams. Crucially, that isn't the mass of the fuel. Okay, that's different. C is just the specific heat capacity of water. You'll be given that number, so that's fine. 4.18 joules per gram per Kelvin. And delta T is obviously your temperature change, and that's in Kelvin. Okay, so 100 grams of water was heated from 23 degrees Celsius to 57 degrees Celsius by 1.8 grams of ethanol. Okay, so we're going to calculate the calculate the energy transferred and hence the enthalpy change of the fuel. Okay, so we're going to use this Q equals MC delta T. Now the mass of water that we use, remember this is the mass of water, not the fuel, is 100 times by 4.18 times by 34, because that's the temperature change. Q basically is going to be 14,212 joules or 14.212 kilojoules. So we're calculating the energy first. Remember, this is in joules. Then what we have to do is then work out the enthalpy. Now remember, enthalpy is in kilojoules per mole. So we need to know the kilojoules bit first, and obviously then we need to work out the number of moles. Now this is the number of moles of the fuel. So moles of ethanol is mass over MR. So the mass is 1.8. As you can see here, we used 1.8 grams of ethanol, and the MR of ethanol is 46. So the number of moles is 0.039. This is the enthalpy change of the fuel. This is the number of moles of the fuel that we've burnt. Okay, so to work out the enthalpy change, we then take the energy that we worked out in the first step, and we take the moles that we worked out in the second step, moles of the fuel, and we divide them. So it's energy divided by moles. Now because this is an exothermic reaction, we put a minus in front of that, so it's minus 14.212 divided by 0.039. That gives us an enthalpy change of minus 364.4 kilojoules per mole. Okay, let's have a look at another example of calorimetry. So the energy from calorimetry, like I say, it can be measured from solutions as well. So like the previous example, we looked at burning a fuel and heating up water. This one we're going to measure solutions. Now this one's a slightly different setup. We're going to have a polystyrene cup instead of a copper can, because we're not actually heating these up. We're going to add an acid in here first, and then we're going to measure the temperature. So this is going to be a neutralization reaction, enthalpy of neutralization. Then what we're going to do is add an alkali or a solid, stir the mixture, stir the solution that you've made, and measure the temperature change. So let's have a look at an example. So we've got 25 centimeters cubed of 1 mole per dm cubed HCl had a temperature of 20 degrees Celsius. 25 centimeters cubed of 1 mole per dm cubed of sodium hydroxide was added, and this raised the temperature to a maximum of 26 degrees Celsius. Calculate the enthalpy of neutralization for hydrochloric acid. Okay, so first thing we need to do is to work out Q, which is the energy change. Now the slight difference here is that we have a total mass of both liquids of 50 grams. We're assuming that the density is 1 centimeters cubed is 1 gram per centimeter cubed. So for every centimeter cubed, which is basically a gram. So we've got 25 of this and 25 of this. Because we've got both liquids in here, we're going to add them both together. That's why we've got the 50. Times it by your heat capacity, 4.18, times it by 6, which is your temperature change when it's increased. And this will give us a value of 1,254 joules or 1.254 kilojoules. So the moles of HCl is just concentration times volume. So the moles of HCl, the concentration is 1, because it's said here, it's 1 moles per dm cubed, this is of HCl, times by 25, times by 10 to the minus 3. Remember, the volume is 25 centimeters cubed, but we have to divide by 1,000 to get it into decimeters cubed. So we just put this times 10 to the minus 3 on to do that. Number of moles is 0.0250. That's what we've just worked out. So once we've done that, then we work out our enthalpy change. So enthalpy is energy divided by the number of moles. So the energy, again, because this is an exothermic reaction, we put a minus in front of it. If it was endothermic, you just keep it positive. 1.254 divided by 0.0250, and that's the number of moles. Enthalpy in this case is minus 50.16 kilojoules per mole. Okay, so make sure you're able to obviously calculate that. So you can see this one's slightly different from the experiment that we've seen just previously. Okay, so we're going to look at Hess's law. Basically, this person called Jermaine Hess, he came up with a law to work out enthalpy changes that you can't find out during an experiment. Okay, so this is obviously going to be pretty useful because chemists like calculating things that they can't necessarily do in a practical. So this is going to be pretty useful. So basically, his law, he stated that the total enthalpy change of a reaction is independent of the route taken. You must remember that law. You may be asked to recall that law and write it as an answer. Okay, so total enthalpy change of a reaction is independent of the route taken. Okay, we're going to look at two types of cycles. The first one is formation. Okay, if the data they've given you is formation, we draw a formation cycle. So you can see here that the data here is formation. You're just looking out for the delta FH data. So look at the table they've given you. If it's formation, you're going to draw one of these cycles. So what you do is you do reactants and products. So you do reactants and you draw an arrow and you put products. So this bit is the enthalpy of combustion or enthalpy of reaction. It depends on the numbers they've given you, but it could be called either of them. Now, the cycle has elements in their standard states at the bottom. These are the elements that make your reactants and products. The arrows going up represent enthalpy of formation. So it's delta FH. So this is the enthalpy of formation. We set our cycle out here and make sure your equations are all balanced as well. So remember, we need to substitute the formation symbols here, okay, for the numbers, and we need to multiply by the number of moles in the equation. That's why it's really important to balance, because we need to multiply these moles. Let's have a look at an example. Okay, so when you go with an arrow, just when you look at this example, it's an important thing to remember, because this is how the cycles work. When you go with the arrow, we keep the sign the same. When we go against the arrow, we change the sign. Okay, and you'll see that in a minute. Okay, so here's the example. Calculate the enthalpy of combustion of methanol burning completely in oxygen to make carbon dioxide and water. Now you can see here, the data they've given us is formation data. So we have to draw a formation cycle like we've just seen before. So all we do is we put our reactants on one side and our products on the other. So here's our reactants, there's our methanol. Burning in oxygen is complete combustion to form carbon dioxide and water. Now we're forming these from elements in their standard states. So we've got carbon, oxygen and hydrogen, as you can see on here. So these are the elements. Make sure they're all balanced as well. Obviously 4 oxygens here in total and 4 hydrogens on here in total. So make sure they're all balanced. So what we're going to do is going to put the number in. Again, we're looking at the enthalpy of formation of methanol. This is minus 234. Notice we don't have oxygen. It hasn't actually changed. So the formation enthalpy changes of elements are always 0. So this is obviously gone from O2 to O2, so there's no change. So the total on this side is minus 234. And on this side, we're going to work out the formation of carbon dioxide first. We're forming 1 mole of carbon dioxide, so that's just minus 394. We're forming 2 moles of water, so we have to do 2 times minus 286, because that's the enthalpy change of formation of water, and that's minus 572. If we add these up, we should get a total of minus 966 on that side. Okay, remember we want to work out the enthalpy of combustion. This is the enthalpy of combustion over here, because this is the burning bit. Sometimes this may also be known as the enthalpy of reaction, but in this case we're going to use combustion. Okay, so we need to work out the enthalpy of combustion, and so we need to take an alternative route. So we go against the arrow via A, and we go with the arrow via B. So imagine it's like a roadblock. We're going from here to here. We can't go that way. So the diversion, so to speak, would be going this way and then up here. So going against the arrow here, and with the arrow here. So let's have a look. Against the arrow, we keep the number the same, but change the sign. So it's plus 234. And then with B, we're going to just keep that the same, minus 966. So that's it there. You literally just put the numbers in. And then if you put that in your calculator, we should get a value minus 732 kilojoules per mole. And that is basically the enthalpy of combustion. Okay, and just a way of testing it, if you start anywhere on this cycle and you go against the arrow, you flip the sign, and with the arrow you keep it the same. Anywhere on this cycle, so you could go here to here and then back again, and put all those numbers in, it should add up to 0. Basically, it's independent of the route taken, the energy. That's basically what Hess's law came up with. See? It all does make sense. Right, okay. Let's have a look at the second cycle. Now, this is combustion cycle. If they give you data that's combustion data, we draw a combustion cycle. So you can see here, this data is combustion data. We have delta CH, enthalpy of combustion. So the cycle looks very similar, except you just need to make sure you get these things the right way around. Reactants and elements on the left, products on the right. Again, we can call this enthalpy of formation or enthalpy of reaction. We can call them either basically on the top, and so just read the question carefully. I'll tell you what to call them. Combustion products are always at the bottom. Notice this time in this cycle the arrows point downwards because it's combustion. So we've got elements, reactants and elements over here, and products over here. We always have combustion products over here, carbon dioxide and water. Remember, the assumption is with this that we burn them completely in oxygen. We get complete combustion, so the only products we'll produce is carbon dioxide and water. Okay. Now remember, obviously we've got all our combustion data here. We're going to use this data substituted for where it says delta CH, and then we multiply by the number of moles as well. Again, we'll look at an example just like we did with the other one. Okay. So again, remember, if we're going with the arrow, we keep the sign the same. If we're going against the arrow, we change the sign. So let's have a look at this example. So calculate the enthalpy of formation of pentane from their elements in their standard states. You can see here that we've got all of our substances there, carbon, hydrogen, and our pentane, which is C5H12. We've got the enthalpy of combustion. Look at the data they've given us. It's combustion data, so we must draw a combustion cycle. So the first thing we need to do is we put our elements here, carbon, hydrogen, oxygen, and then we're going to obviously form our pentane and oxygen. Okay, now notice you've got O2 and O2 on the same side. Effectively, we can cancel these out. They will cancel out. It's just there to show combustion. But yeah, we can get rid of them, so we can just ignore them. Okay, so because it's combustion, we have carbon dioxide and water on the bottom, and we have our arrow pointing down. So we're going to do combustion of carbon first. We've got 5 carbons, so it's 5 times minus 394, and that's going to give us minus 1970. We have to do combustion of hydrogen as well. We've got 6 of them. 6 times minus 286 is minus 1716. And so the total enthalpy of combustion on the left is minus 3686. Okay, on the right hand side, we're going to do combustion again. We can just ignore the oxygen bit because they cancel out left and right, so we just ignore them. But we've only got one here, which is just pentane. So because we've only got 1 mole of that, it's just going to be minus 3509. So the enthalpy change of combustion on this side is minus 3509. Okay, and remember we want to work out the enthalpy of formation. This is elements going to your obviously pentane here. Notice we're not drawing a formation cycle, even though it's asked us to work out the enthalpy of formation. Our data is combustion, so we must draw a combustion cycle. Again, just like before, to work out the enthalpy of formation, which is this bit here, all we need to do is take an alternative route. So we go with the arrow with A this time, and against the arrow at B. So you want to get from here to here. Imagine this is like closed off, a bit like a roadblock. So the alternative would be going with the arrow here and against the arrow there. So let's put the numbers in. With the arrow, you can see minus 3686, we just keep it the same. And then against the arrow, same number, different symbol in front, so that's plus 3509. And then we get a total enthalpy of formation of minus 177 kilojoules per mole. Okay, now this is the enthalpy change. It's an exothermic reaction. And again, just test it. Start anywhere on the cycle, just like before. If you keep and just go round the cycle. Remember, if we go with the arrow, you keep the sign the same. If you go against the arrow, you change the sign. add it all up, and it should add up to 0. Okay, and that's it. That is a overview of Energetics 1 for topic 8 for EDEXCEL. Please subscribe to this channel. It's a massive support. It's a real kind of enjoyment really to produce these videos and help people. But show your appreciation just by subscribing. That's all we really need, to be honest. So we just click on that middle button in the middle, and you can subscribe using that. And just a quick reminder that if you'd like to access these slides and have them on have a personal copy on your computer or tablet, then just click on the link in the description box. They're great value, so fill your boots. That's it. Bye bye.